Style machines are probabilistic models that can generate animation data in a broad variety of styles. Style machines are learned from data. Instead of learning a single model of the data, we learn a low-dimensional manifold of models that spans all the stylistic variations in the data. Each point on the manifold indexes a unique model. Every model captures a different style. The dimensionality and coordinate system of the style manifold are determined automatically. In this video we show animations generated from a style manifold of path maps. A path map is a probabilistic model that infers the behavior of a target system X from observations of a Q system Y. The mapping may be very ambiguous. For example, path maps have been used to infer facial motion from voice data and full 3D body motion from shadows. A path map interprets the behavior of a Q system in terms of qualitative states of the target system. Every possible state sequence is assigned a probability according to its global consistency with the entire Q time series and with the qualitative dynamics of the target system. From this distribution over state sequences, we can synthesize an optimal target time series. Here we will use a learned style manifold of path maps to synthesize virtual motion capture. By sampling path maps at different coordinates on the style manifold, we can resynthesize motion data in a variety of styles. The outputs are sequences of raw marker positions, which we have rendered as skeletons. However, the bones are purely decorative and have no algorithmic content. We begin with some style analogies. For example, walking is to running as strutting is to what? We solve these analogies by completing the parallelogram on our learned style manifold. Here are the three given corners: walking, strutting, and running, which the style machine resynthesizes as a strutting run that looks like high-speed skanking, a dance form. Here's another analogy with walking, the catwalk of a fashion model, and running, which is then resynthesized as cat running. Of course, walk cycles and motion primitives are relatively easy. Let's consider resynthesizing entire performances. Here is a valiant attempt at ballet by a graduate student. After stumbling, losing the beat, and missing moves, he decides to keep his day job. We'll resynthesize this data with a style machine that has been trained on some highly skilled performances in a variety of ballet and modern dance styles. Here are relevant snippets from two of the training sequences. The choreography is similar, but the motions are quite different. The learning algorithm discovers their correspondence. Here is our novice's performance, resynthesized in an artificial style that lies near those of the two skilled performances just shown. Shorebeat's taking lessons. Style machines can be driven by data other than motion capture. Here we show some animation generated from a sequence of shadows. Here is the sequence of silhouettes, computed from video using simple vision algorithms such as back subtraction. Here is an initial 3D reconstruction. Here is a more stylized balletic version of the jump, and this was synthesized from style coordinates taken closer to that of modern dance. A style machine can generate new, plausible choreography by doing random walks on its internal state machine. Essentially, it's being driven by noise. Here's some random choreography synthesized in a style near our ballet sample, but far from our lazy ballet sample. Here's the same choreography synthesized in a more modern style, but slightly lazier and with more mannish body dynamics.